Dear student, I am Dr. Harold Thomas, Professor in Applied Geology, Department of Applied Geology, Dr. Hari Singh Gaur Vishwavidyalaya, Sagar. Today, in this course, I will deliver my lecture on silicate mineral classification. It is just for revision of your undergraduate course because mineralogy is a backbone of petrology. In this lecture, I will proceed under the following heads: introduction, structure of silicate crystals, silicate structure, classification, nesosilicate, sorosilicate, cyclosilicate, inosilicate, phyllosilicate and tectosilicate with example, etc. I will cover this topic in 3 parts so that it will be good for the student to understand the whole topic properly. Hope it will be useful for you before embarking upon the main topics of the paper, that is metamorphic petrology and thermodynamics. Since silicate minerals make up almost all the earth crust and mantle, it is important to understand their structure, composition and properties. The structure of the silicate mineral is very important to understand their properties and also the properties of rock usually formed by the combination of these silicate minerals. Therefore, a very clear understanding of silicate structure is required. We know that magma is a complex silicate melt and different igneous rocks are usually formed by the crystallization of magma. Later, igneous rocks, after weathering, erosion and transportation of sediments, gradually subside in geosynclinal basin at greater depth, change into sedimentary rocks. Igneous and sedimentary rocks transfer into metamorphic rocks with certain specific changes under the influence of pressure and temperature conditions. Petrologists who are interested in geothermometry and geobarometry usually calculate the pressure temperature condition of equilibrium and always appreciated the knowledge of crystal structures where cations at a particular site is important. Therefore, the silicate classification, which are dominant constituents of a different rock type, is considered here in this paper. The student who are interested in detailed studies of mineralogy can follow the standard book of Dana, System of Mineralogy, Rock Formation Minerals by Deerhove and Jussman, Manual of Mineralogy by Keel and Herbert Jr. and other books, e-contents and different research journal, etc. The silicate minerals usually contain Si and O with ionic bonds. The SiO gives a tetrahedral units of all the silicate structures because the silicon ions are in 4-fold coordination with oxygen. In silicate, individual tetrahedra are joined by sharing of apical oxygen and maximum 4 oxygen is possible. This sharing or linking of the silicate tetrahedron give rise to different silicate types or different silicate minerals. It is important to note that ionic radius of oxygen O equal to 1.4 angstrom and silicon Si equal to 1 angstrom. In the specific crystal structure, one can show tetrahedrons with a specific symbol of a tetrahedron or exhibit by ball and spokes models. The student should also understand that the tetrahedra SiO4-4 as polyhedron are electrically neutralized by cations and make stable configuration. The cation's arrangement in the crystal structure is ruled by their ionic radii and by their valency stable. In this lecture, we will confine to the most important example of silicate minerals, starting with the nesosilicate and last with framework structure. The silicate minerals has been classified based on different linkages of silicate tetrahedron, which we will discuss here. Single tetrahedra or independent tetrahedra group, nesosilicate or orthosilicate. In this type, SiO tetrahedra are present as separate entities. The resulting composition is SiO4. This is known as nesosilicate or orthosilicate. The nesosilicate means neso equal to Iceland. The important examples of different minerals group crystallized under this silicate structures are as follows. Olivine group, first MgFe SiO4 olivine, Mg2 SiO4 phosphorite, Fe2 SiO4 fayalite. Garnet group, Pyroxene series, Fe plus 2 thrice Al2 SiO4 thrice almandine, Mg3 Al2 SiO4 thrice pyrope, Mn plus 2 thrice Al2 SiO4 thrice spessartine or spessartite. Garnet group, uranidite series, Ca3 Cr2 Si3O12, urovite Ca3 Al2 Si3O12 gracilorite, Ca3 Fe plus 3 Ti twice Si3O12 andradite. Aluminosilicate polymorphs, Al2O SiO4 or Al2 SiO5 kyanite, Al2 SiO5 sillimanite, Al2 SiO5 andalusite. Zircon, Zr SiO4 zircon, staurolite, Fe Al4 Si2O10 OH twice. Topaz, Al2 SiO4 FeOH twice. Sphene, CaTiO SiO4. The nesosilicate form from high temperature fluid magma, providing the magma has a sufficient content of neutralizing cations. The nesosilicate follow the following rules that highly charged cation Si4 plus maintain as large as a separation is possible. Hence, tetrahedra does not need to polymerize and share common oxygen. Plenty of other cations are present to maintain electrical neutrality. The stability of the six-fold MgO or FeO octahedral linkages between adjacent tetrahedra oxygens is thus enhanced by the better fit of Mg or Fe in the expanded octahedral space. In olivine and garnet, cleavage is irregular because of the isolated tetrahedral structure produce no preferred plane of weakness. Double tetrahedra structures or sorosilicate. In the sorosilicate groups, two of the tetrahedra are joined together. Two SiO tetrahedra are linked by sharing of one oxygen between them to form a double tetrahedra unit. The resulting composition is Si2O7 minus 6, and the silicate structure formed by this shared tetrahedra is known as sorosilicate. Soro equal to group. Examples: first, Ca Al2 Si2O7 OH twice S2O. lawsonite, Zn4Si2O7 OS twice S2O, hemimorphites, Ca2Mg Si2O7 millilite, and Ca2Al3 Si3O12 OS twice epidote. Cyclosilicate, cyclo equal to rings. In this case, 2 of the oxygen of each tetrahedra is shared with neighboring tetrahedra. The regular position of tetrahedra are such that closed unit of the ring structures formed ring of 3, 4 or 6 tetrahedra are known. For example, 3-member rings, example BaTi Si3O9 bentonite with 3 linked tetrahedra Si3O9 -6. 4-member rings, for example CaMnFe thrice Al2 BO3 thrice Si exenite with 4 linked tetrahedra Si4O12 -8. 3-member rings, example Ba3 Al2 Si3O12 beryl with 3 linked tetrahedra Si3O9 -12. Chain structure, inosilicates. In chain structures, the SiO4 tetrahedra share 2 of their corners with the neighboring tetrahedron to produce infinite chain with the composition SiO thrice N bracket close N. This type of silicate structure is known as inosilicates. Ino equal to chain in Greek. The chain are infinite in extent and are elongated usually in the C direction of the crystal. On the basis of the different combination of the chain, the inosilicates are divided into following types. First, single chain, pyroxene and pyroxenite type. The SiO4 tetrahedra share 2 of their corners with neighboring tetrahedron to produce infinite chain in which SiO ratio is 1:3. The single chain therefore has the composition SiO thrice N -2. The examples are pyroxene and pyroxenite. Orthopyroxene or orthorhombic, MgFe pyroxene, Mg2 Si2O6 inositide, Fe2 Si2O6 ferrocellite, MgFe twice Si2O6 hypersthene. Monoclinic pyroxene or clinopyroxene or calcium pyroxene, CaMgSi2O6 diopside, CaFe+2 Si2O6 Heidelbergite, CaFe-Mg-Al twice Al-Si2O6 augite, Mgfe+2 Ca Mgfe+2 Si2O6 pisonite, sodium pyroxene NaFe+3 Si2O6 azerine, NaAl-Si2O6 jadeite, lithium pyroxene LiAl-Si2O6 pseudomelanin, triclinic pyroxene. Triclinic pyroxene Mn2 Si2O6 rhodonite, Ca2 Si2O6 wollastonite. Double chain, the alternate tetrahedra in 2 parallel single chains are cross-linked. The silicon oxygen ratio is 4:11 and the double chain has the composition Si4O11 -6. For examples, amphiboles. Mineral orthorhombic amphiboles, anthophyllite MgFe7Si8O22OH twice, gaderite MgFe5Al2 Al2Si6O22OH twice, monoclinic amphibole cummingtonite MgFe7Si8O22OH twice, grunite Fe+2 Mg7Si8O22OH twice, tremolite Ca2 Mg5Si8O22OH twice, actinolite Ca2 Mg5Si8O22OH twice, hornblende CaNa MgFeAl728 AlSi8O22OH twice, glaucophene Na2 MgFe thrice, FeAl twice, Si8O22OH twice, rebecite Na2 Fe+2 thrice, Fe+3 twice, Si8O22OH twice. The inosilicates are further subdivided on the basis of crystallographic symmetry, orthopyroxene or orthoamphiboles showing the orthorhombic symmetry, and clinopyroxene and clinoamphiboles showing the monoclinic symmetry. J.B. Thomson in 1970 discovered from the Chester area in Vermont, New Hampshire state, two other type of chain structures called triple chain and mixed chain. In triple chain structure, single and double chains are cross-linked and composition is Si6O16-8 or Si3O8-4, that is with the SiO ratio is 3:8. Veblen and Braham 1975, for example, orthorhombic James-Thomsonite MgFe10 Si12O32OH4, monoclinic James-Thomsonite. The chain consists of alternate double and triple chain, but the two types are not cross-linked. The composition of the mixed chain can be found out from a mixture of double and triple chain composition. Si4O11-6 plus Si6O16-8 equal to Si10O27-14. For example, chesterite with orthorhombic symmetry and unnamed mineral crystallize in monoclinic system. Both ortho and monoclinic system minerals have the composition MgFe17 Si20O54OH6. The triple chain and mixed chain structures are structurally intermediate between the amphiboles and micas. This group is characterized by seat structures. The 3 oxygen of each tetrahedra are shared with adjacent tetrahedra to form extended flat seats extended in 2 directions, remaining apical oxygen points towards you. This apical oxygen generally bonds with others octahedrally coordinated cations. Different stacking arrangement of tetrahedral seats and octahedral seats, along with the type of cations that occupies the octahedral site, allow for the variety of phyllosilicates that occur in nature. The SiO ratio is 2:5 and it is fundamental unit in all micas and clay structures. The seat form hexagonal planar network and responsible for phyllosilicate, phyllo equal to seed. Octahedral varieties includes dioctahedral. Cation in octahedral seed is trivalent plus 3, usually Al plus 3. The -6 charge from the anion is satisfied by only 2 trivalent cations. Therefore, 1 out of every 3 cation site is vacant. Each O or OH is bounded to 2 cations. Trioctahedral cation in octahedral seeds are divalent plus 2, usually Mg or Fe plus 2. The -6 charge from the anion is satisfied by the 3 divalent cations. So, all cation sites are filled with each oxygen or OH is bounded to 3 cations. Example of phyllosilicates: mica type or 10 angstrom type. In this type, there is a layer of octahedral coordinated cations sandwiched between 2 identical tetrahedral layers with apex of tetrahedral pointing towards each other. The repeat distance is 10 angstrom along C direction, have a T O-T stacking patterns, tetrahedral seeds for every 1 octahedral seeds. Alkali mica, muscovite, white mica or potassium mica, KAl2, AlSi3O10 OH twice. Paragonite, soda mica, NaAl2, AlSi3O10 OH twice. Trioctahedral mica, lepidolite, lithium mica, KLi2, AlSi4O10 OH twice. Zinwaldite, lithium mica, potassium under bracket lithium, iron bracket close, AlSi4O10 OH twice. Phlogopite, magnesium mica, KMg2 AlSi3O10 OH twice. Biotite, black mica or MgFe mica, KMgFe thrice AlSi3O10 OH twice. Phyllosilicates, kaolinite type or 7 angstrom type, 1:1. In this, 1 tetrahedral layer is shared with an octahedral layer. The resulting structure is 2 layered and repeated distance is 7 angstrom, have a T-O stacking pattern, 1 tetrahedral seat for every 1 octahedral seat. Dioctahedral kaolinite Al2 Si2O5 OH4. Trioctahedral talc soapstone Mg2 Si4O10 OH twice. Serpentine Mg3 Si2O5 OH4. Phyllosilicate, chloride type or 14 angstrom type. It consists of 2 octahedral layer and 2 tetrahedral layer and repeated distance is 14 angstrom. Chloride Mg5Al, AlSi3O10 OH8. Tectosilicate or silicate or framework structure. In tectosilicate, tecto equal to framework, SiO4 tetrahedra share all its corner with other tetrahedra, form a 3-dimensional network in which SiO ratio is 1:2. The various form of silica SiO2, namely quartz, tridymite, cristobalite, have the network arrangement in SiO4. The positive and negative charges are balanced. In silicate of this type, structure of silicon is partially replaced by Al plus 3 and the combination is SiAlO twice. The substitution of Al plus 3 for Si plus 4 require additional positive ions in order to restore electrical neutrality. For example, orthoclase KAlSi3O8, albite NaAlSi3O8, naphthalene NaAlSiO4, etc. Silica group, quartz SiO2, feldspar group, orthoclase KAlSi3O8, microcline KAlSi3O8, albite NaAlSi3O8, plagioclase. Plagioclase series NaAlSi3O8 to CaAl2 Si2O8. Feldspathoid group, lucite KAlSi2O6, naphthalene NaAlSiO4, sodalite Na8AlSiO4 6Cl2. Zeolite group, hollandite CaAl2 Si7O18 6S2O. Stabilite CaAl2 Si7O18 7S2O. Lomentite CaAl2 Si4O12 4S2O. Analcine NaAlSi2O6 S2O. Natrolite Na2Al2 Si3O10 2S2O. Dear students, today we have discussed in this lecture about the phyllosilicates and tectosilicate with example, etc. Hope it will be useful for all of you before embarking upon the main topic of the paper, that is metamorphic petrology and thermodynamics. I believe this lecture was useful for you to revise your mineralogy, which is important to understand the petrology. For further studies, please read the books and references given in the text. Thank you very much.